Hey guys, so today we are starting multiple linear regression. It is basically just an extension of what we already know, our simple linear regression model, y equals beta naught plus beta 1x plus epsilon, our random error term, right? A model relating x to y, right? Using x to try to predict y, and where we have our regression coefficients, the intercept and the slope, beta naught and beta 1, and again our random error term where we have assumptions that the random error terms are independent and identically distributed, normal distributions with zero mean, and some variance sigma squared that is the same for each error term, right? For each epsilon I, for I is equal to 1 to n, where n is the sample size, right? For each observation, we assume this is true. So the only difference is that instead of having one predictor variable, one covariate, we have many, okay? Two or more, right? In this case, you could generically denote it k. If that's the case, then we would still have y is equal to beta naught plus beta 1x1 plus beta 2x2 dot 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 plus beta kxk, and again plus epsilon. So um, one cheesy example that I gave you is relating right height to weight. Okay, so the only difference now is instead of just relating height to weight, we could throw in a person's age or their gender, etc., right? And each of those could be the x's. Okay, so we just have multiple predictor variables, right? And independent variables, whatever you want to call them. And we want to relate those, use these group of variables, these group of different x variables, in order to try to gain information about y, okay, our response variable still. Okay, that's so the premise of it is it's really no more complicated than that. Okay, and a lot of the math we're really not going to get into. So for the purposes of this class, I think understanding multiple linear regression really isn't all that uh, much more difficult than understanding simple linear regression. Okay. Okay. So as before, we assume the covariates are kind of known measured values, okay, so that they're not random. And so the least squares estimation, that is still the procedure that we do in order to try to come up with estimates for these parameter values, right? These betas, we want to put hats on them, right? We want to find numbers for these estimates. And so this least squares is the same method, okay? Now technically, this involves what's known as well, in general, the theory behind this involves linear algebra, which is basically matrix algebra, which is not a prerequisite for this course, so there's really no point in me going into this. But if you're familiar with that, you could look at this sort of thing. But okay, here we go. So here we still have our Q, which is for our least squares equation, and it's still nothing more than the sum of the squared residuals, okay? Still nothing more than that, where basically y, right, our observed value, and then again this beta naught plus beta 1x1 plus beta 2, that's nothing more than basically what our model is going to predict, right? It's just now we have multiple predictors. Before we just had beta naught plus beta 1x, but now we just have, multiple variables that we can use to try to predict y. So we just stick all of them in there. But it's the same thing. We want to minimize this, right, with respect to these betas. So the only difference now is, right, we have to take the derivative with respect to all these betas and set them all equal to 0 and solve them, right? And then that gives us our estimates. But as before, we didn't do it by hand when we had one variable, so we're certainly not going to do it by hand when we have multiple variables. We can just let R do it for us, okay? I guess one unfortunate thing when we have multiple variables is we no longer have the nice graph. Okay, before, right, we had just we had X, we had Y, we had a scatter plot, right, for X and Y, and then we could fit our regression line through the set of points, okay? And right, we're minimizing the distance between each point in the line. Unfortunately, we're basically doing that same thing, but when we have multiple predictors, right, we have lots of X's, so the dimension of the predictor space, we can't graph it because there's lots of predictors, okay? So one thing, if you had two predictors, you could basically look at it in a 3D graph, right? Because then we would have three different dimensions. But once you have three or more predictors, you couldn't even look at it really graphically. So we kind of lose the nice visual of it, okay? But kind of the sense is still there of we're spitting kind of you can just think about it more of as some imaginary regression line or regression curve, and we're trying to get it as close as possible to all the points. We just can't really picture it anymore because you can't picture things in more than three dimensions really. So that's something to keep in mind, as you can't be thinking that we're going to have this nice graph like we did before for simple linear regression, because we can't. Okay, again, all of this matrix stuff, not worried about. Matrix, 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 okay. And again, matrix stuff, not worried about this. Okay, we're going to have R give us all of the estimates, the beta naught, or the beta hats automatically. Okay, again, estimating the error variance, right? An estimate for the sigma squared. Well, this again is no more complicated than it was before. You take the residual sum of squares of the error sum of squares, which is still nothing more than the sum of the squared residuals, y minus y hat, right? This kind of the hat is once we've actually calculated these estimates, these beta naught or these beta hats. Okay, and then you take that and divide it by its degrees of freedom, and then you get the error mean square, right, or the residual mean square, and that's an unbiased estimate. Okay, before, if you recall, we had, just kind of look at this code, we had just n minus 2 was degrees of freedom, right? But I said 2 specifically was the number of parameters for simple linear regression. That's just beta naught plus beta 1. Okay, in general, it's n minus p, where p is the number of parameters. So, for example, if we had two predictor variables, then we would have beta naught, beta 1, and beta 2. So then p would be 3. Okay, and so you just have to divide it by the sample size minus 3, and so on. Okay, but this quantity is still an unbiased estimator for that variance. Okay, and of course, standard error, right? Standard deviation of an estimator, you just take the square root of the variance and to get that. Okay, breaking down the sum of squares. Don't think we're going to do that. We're not going to pay much attention to that. Okay, so this overall F-test is very important for us. And I think I'll just we'll just see it in an example. I think is a good place to go over that. Okay, I think we've at least talked about enough that I want to go ahead and go over an example. So if we have R up and our ANOVA regression code, go ahead and attach the IRIS data set. Okay, familiarize ourselves with it. We have 3 different species of flowers, and we have 4 observed variables. Length variables, width variables, 2 relate to petal, and 2 relate to sepal. Okay, some other aspect of the flower, I guess. And we saw in simple linear regression, we wanted to relate a petal's width to its length, right? We're interested in its length, and so we want to use its width to predict its length. But we have these other two variables too, right, that are measured on the same set of flowers. And so with multiple linear regression, it allows us to use this additional information, okay, because it's just sitting there completely ignored by the simple linear regression model. So now the goal is still to try to understand the petal length of a flower, but now not only can we use the petal width, but we can also use the sepal width and the sepal length, right? These additional variables, this additional information, we want to use this set of information, these three variables now, okay, three variables, in order to gain information still about petal length. So when you want to put it, you put it in this exact form. So again, I'll just call it reg.model, linear model. You put your y variable here first, you put a tilde, and then you put your x variable just like you did before. And when you have multiple ones, you just separate them by plus sign. Okay, petal width plus sepal width plus sepal length. Okay. And doing that, now we can do all of the same stuff that we did before. Again, before we had this nice plot between the two variables. Now, one thing that you might want to do when you have a set of variables like this, you could still create scatter plots of, for example, petal width and petal length, sepal width and petal length, and sepal length and petal length, right? A scatter plot relating the y on the y-axis and each individual x on the x-axis, so three graphs, three scatter plots. That would just give you kind of an idea of the relationship possibly between kind of each pair, right? But in the end, that's really not kind of the full model, but could be something to just at least give you some visual, okay? So let's look at what this model looks like. Okay. So it looks like now, right, y hat is equal to negative 0.26. Okay, I'm just going to round because plus 1.45 times x1. Okay. Plus negative 0.65 x2 times x2 and 0.73 times x3. Okay. And of course, just to reiterate, so we've got petal length is equal to negative 0.26 plus 1.45 times, and of course, if you want, you can put the times just to 1.45 times petal width minus 0.65 times sepal width plus 0.73 times must be sepal length. Okay, so this is our regression equation, right? Of course, now it's in 2, 3, 4 dimensions, so we can't even see it in a graph. But the kind of the logic flows from simple linear regression, what we're trying to do. This time, this is still considered our intercept, okay, beta naught, or in this case, right, we have hats, beta naught hat estimates. This is still the y-intercept, okay, but now it's not just when x is equal to 0, it's when x1 is equal to 0, and x2 is equal to 0, and x3 is equal to 0, okay? So in this case, it would be saying that the estimated petal length of a flower that has 0 petal width, 0 petal width, sepal width, and 0 sepal length is this, which of course doesn't make sense. So that implies in this example that the intercept is not something that's very interpretable or useful to us. But these other betas are, okay? So these are still, in this nice case right here, we can still consider these slope parameters, okay? So I basically just said what this is, right? When all the x's are 0, we expect a petal length of negative 0.26, okay? So that's interpreting our beta naught hat. Okay, beta 1 hat. Okay. It is still the slope parameter relating petal width to petal length, but we do have to take into account these two, which I will do. So I'll write it like this. For every 1 unit increase in a petal's width, we expect the petal's length to increase by 1.45 units. Again, we don't really have units for this data set, just whatever the length variable is, could be centimeters, etc. Okay. So for every 1 unit increase in a petal's width, we expect the petal's length to increase by 1.45 units with the other variables held constant. Okay, and that's a line that extra sentence or extra part of the sentence that we need to distinguish the multiple linear regression model. So what it means is if we change petal width by 1, right, petal length changes by the slope parameter just as it did before, but as long as we're holding these other things constant. Okay, we're not varying the sepal width and sepal length at the same time. Okay, and it's basically the same thing for the other thing. For every, okay, so for every 1 unit increase in the sepal width, right, a sepal's width, I should maybe put the sepal width of the flower or whatever, okay, we expect the petal's length to, notice it's negative, right, we can't forget that, decrease by 0.65 units, again with the other variables held constant, okay? And then the slope for the third is pretty obvious, I think. Whenever we increase a sepal's length by 1, we expect the petal's length to increase by 0.73 units, provided we hold the other variables constant. Okay, so basically just trying to say if we change this one variable and don't change the other variables, right? We don't care what value they have. Okay, we don't care what value they have as long as we're not changing those at the same time we're changing this. Then for every 1 unit increase in this, right, the response variable changes by the slope. And that same interpretation holds for any number of predictors that we might have. Okay. Okay. So the plot, right, not really useful unless you want to do it for each variable just to get a visual. And in this case, this right here, this should be already because this was still our response. Okay, and these are our fitted values, and we're actually still using the same, actually, see, I made a mistake there. Okay. The degrees of freedom is not 2, right? It's 4. There are 4 parameters. Beta naught, beta 1, beta 2, beta 3. 4 parameters. Okay. So that doesn't look like it really did much, but nonetheless, this is our estimate. And as before, we don't really have to do that, and I don't really expect you to do that. If you just put ANOVA, do we still have it? Okay, actually, so you can still get it from here. The residual mean square is still correct. Okay. Notice it's just giving you more quantities, but we didn't really go into those so much anyway. So, so you can just ignore those and you can still get the estimate here. Okay, and to 2 decimal places anyway, it's 0.10. Okay. All right, what else can we look at? We could look at confidence intervals for each of the parameters, right? And I'm not going to go through each of those, but the general gist is the exact same. So for example, I'll just take petal width. So for every 1 unit increase in beta 1, right? So sorry, for every 1 unit increase in a petal's width, right, our beta 1 parameter, or which relates petal width to petal length, we expect a petal's length to increase between 1.3 and 1.5, right? And we're 92% confident of that, provided the other parameters are held fixed. Okay, so basically you take the exact same interpretation of the confidence interval that we had before and just throw in the extra sentence, provided we hold the other variables constant. Okay, that's all you have to do. Okay, because we're basically just trying to say, I want to look at the relationship between this single variable and the response right now, right? I don't want these things to be changing. Okay, one at a time, if you will. Okay, summary. Okay, lots of stuff. Okay, here are beta naught, or I keep saying beta naught, our beta hats, okay, our estimated regression parameters. Here are p-values. Just like before, this is the p-value testing the hypothesis whether beta naught is equal to 0. This is the hypothesis testing whether beta 1 is equal to 0. The only thing is, now we have a couple more parameters, right? A couple more regression parameters. So now this is just the hypothesis p-value testing whether beta 2 is equal to 0 and beta 3 is equal to 0. Okay. Besides that, nothing more is going on. Okay. So here's a good point that I want to make. It's a little bit different. Something is a little bit different now. Okay. So almost always there's not a whole lot of reason to look to see whether you could drop the intercept or not, okay? But technically this is saying that you couldn't, right? This is what this p-value, just assume alpha is 0.05, right? This p-value is greater than 0.05, so we would fail to reject the null hypothesis, which in this case is that beta naught is equal to 0. So failing to reject the null hypothesis, that beta naught is equal to 0. So we don't have evidence that it's not equal to 0. Okay, so and we take that usually in modeling to mean, well, it's probably not needed then. Well, in this case, but that's the thing, it's 0. That's just not useful. Okay, what we want to test is these. Okay, right? Because these p-values tell us whether we need these variables in the model or not. Okay, so for example, this one, as before, okay, all these three of these p-values are the same, right? 2 times 10 to the negative 16th. So they're both, all of them are basically 0. So in each case, we're going to reject the null hypothesis that that the parameter 0, so beta 1, we reject that beta 1 is equal to 0. And so we have evidence that it's not equal to 0, and thus we have evidence that petal width is related to petal length. Same thing with sepal width, same thing with sepal length, right? You take them one at a time. One thing I will say, if we have a large p-value, right, larger than alpha in one of these intercept, or in one of these slope parameters, if we have it in one of them, then right, so kind of take this large p-value and stick it in one of these that we actually care about, maybe this last one. If that p-value is greater than alpha, then that says we don't have evidence that beta 3 is not equal to 0. So kind of it might be equal to 0. And so, in other words, it doesn't appear that sepal length is useful. And thus, we can kick it from the model to make the model a little bit simpler. Right? Simple models are better than larger models if they have the same or relatively the same performance. But one thing that you cannot do from these p-values right here is kick more than a single variable from the model. For example, if these two, or pick any two of them, if any two of them have big p-values, right, say bigger than 0.05, you cannot from these p-values determine that those two variables can be kicked from the model. You can only determine if a single variable can be kicked from the model. So if a single one of these had a high p-value, you could kick it from the model. But if more than one has a high p-value, you cannot remove it from the model. What each of these p-values is, okay, it is testing whether, it's basically testing whether this variable is useful or not. But we have multiple variables now, so there's kind of an additional statement, okay? It's testing whether, say, we'll just take beta 3, is testing whether kind of x3 is useful in the model that already contains the other two predictors, okay? So it's saying, is x3 useful if my model already contains x1 and x2? And likewise, this beta 1, or this p-value for beta 1 is testing, is x1 useful in a model that already contains x2 and x3? So sometimes multiple predictors can kind of try and basically be measuring the same quantity, okay? And if that's the case, it could be that once you include one of those predictors, the other predictor doesn't really do much. And if that's the case, what you could see is you could see, say, two large p-values here, because each of these p-values is saying, well, I don't need this one if I already include this one, and likewise this one's saying I don't need this one if I already include this one. Okay, just kind of assume those are big. And if that's the case, you would just kick both of them out of the model, all right? But you can't do that because the model could need one of those. It's just that whenever you include both, each one is kind of saying, well, now that I have this one, I don't need this one, okay? In order to determine if you can kick more than one thing out of the model, you have to do what's called a partial F test. Okay. It's not horribly difficult to do. It has to deal with some of these sum of squares. Okay, you've got to divide a couple things by its degrees of freedom. I'm not going to show you that in this class because we've lost some time, but I do want you to know if you were ever to do this and you had two things or more than two things and which had high p-values, you cannot simply kick them out. But there is one thing. Let's say that all three of these had high p-values. Okay, all three of them, meaning, right, it doesn't appear that any of them are useful. Okay, that's basically in this regression setting that we're doing a high p-value, right, suggesting that maybe that parameter is equal to 0. Well, again, if that parameter is equal to 0, that slope is equal to 0, then that means that the variable, the x variable, is useless. Okay, so if all three of these had high p-values, again, in this real example, these are all low, but if these were all high, then that would be suggesting that none of them are useful. But again, you cannot just see that and kick them out. But there is, from this output, I would not, you have to do a partial F test if, say, you wanted to kick 2 out for high p-values. But if all three have high p-values, you can look down here to determine if you can kick everything out of the model. And of course, kicking everything out of the model, what does that mean? That means basically this set of predictor variables is not useful in predicting your response. So basically kind of the model's useless. That's a easy way to think about it, right? If none of these predictors are useful in predicting the response, then the model's kind of useless. So again, assume all three of these had high p-values, just say greater than 0.05 if that's what significance level we wanted. You can't just say, okay, they're all useless, kick them out, my model's useless. Look down here. This is what allows you to tell this p-value right here, okay, the p-value right here given at the bottom of the summary function is the p-value, okay, which tests the specific hypothesis. This is the overall F-test. Okay, we did see that in the notes. I skimmed through it. If you look, you can see it in the notes. It's testing the hypothesis that beta 1 is equal to beta 2 is equal, in this case, beta 3. Okay, notice I didn't include beta naught. The intercept, again, is useless. It doesn't contain information about these. Okay, beta 1, beta 2, and if you had more predictor variables, you would just keep tacking them on. Okay, is equal to 0. It is a test whether all of your predictor variables, right, or the regression parameters which go with them are equal to 0. Okay, that's what the overall F-test. So it's, in other words, right, i.e. tests whether any predictor variables are useful. Okay. And of course, as usual, the alternative hypothesis is the opposite, which would just be at least one is not equal to 0. Okay, doesn't say which one, it just says at least something in the model is useful. Okay, so the overall F-test, this p-value, is testing whether beta 1 is equal to 0, beta 2 is equal to 0, and beta 3 is equal to 0. Okay, and of course, well, these are all small, so we don't actually need it in this case. The only time you would need this is if all three of these were big, right? Meaning individually looking like none of them are useful. But again, you can't kick more than one thing out of the model with these p-values alone. But this p-value tells you whether you can kick all of them out. And it's low, right? Thus, something in the model is useful, right? If this is less than alpha, so we would reject this, right? So at least one is not equal to 0. So at least something is useful in the model. But again, this cannot tell you, say, pretend beta, this p-value, the last two p-values are large. Okay, it cannot test whether these two can be kicked out. It only tests all three. Okay. So in order to test 2, you would have to do that partial F-test, which again, I'm not going to cover in the class. Okay, there's something else important in this table, which is R squared, okay, which is called the coefficient of determination. And it is right here. It's called multiple R squared. So the coefficient of determination, R squared, right, it's going to be between 0 and 1. Okay, it has to have a value between 0 and 1. And what it is interpreted as is it's the proportion of variability in the response variable that is accounted for by your model, okay, basically by your set of predictor variables. So in this case, we can see it's 0.968. So I want to interpret this multiple r squared in this context. So together are my three predictor variables: sepal width, petal width, sepal width, and sepal length account for 96.8% of the variability in the variability of a flower's petal length. Okay, my set of predictor variables, right? These are my three predictor variables, account for almost 97% of the variability in the response, the petal's length. Okay, so as we can see, it has to go between 0 and 1. 1 means that it accounts for 100% of the variability. That is basically a deterministic model. That's kind of like having that correlation of 1, right? Kind of a perfect relationship. Okay, so in general, the higher the multiple r squared, the better your model, right? Just logically speaking, the higher this is, the more of the variability in the response variable that we have accounted for by the model, right? So the better it's basically the better we're able to model the response. That's in general, that's what it means, and in most cases you won't go wrong by thinking about it like that. But I do want to point out that if this is high, it doesn't mean that the model can't be improved or that the model is necessarily right. Okay, it could be that it looks like this is accounting for a lot of the variation, but that that there's still something wrong. Okay, it doesn't tell us whether the assumptions on the model are correct and that sort of thing. Okay, or that there's something that the model needs. Okay, but in general, the higher r squared, the better this is. One other thing, notice it is r. If you remember the correlation, which we denoted little r, technically this coefficient of determination is little r squared. It is the square of the correlation. Okay. Notice that it goes positive, right? So you wouldn't be able to tell whether, well, that's in the simple linear regression case. That's in the simple linear regression case. Okay. But in the multiple linear regression, you don't have that correlation anymore. And as before, you can do prediction intervals and confidence intervals for the mean value, okay? And the only difference is, maybe I'll go ahead and put it here. Okay, we would need to, you could predict the response. The only difference is we've got 3 x's in the model. You would have to put petal width is equal to something, right? Some value of interest, comma, sepal width is equal to something, comma, sepal length is equal to something. And then it would give you either a confidence interval or prediction interval for the petal length for a flower which has x1 is equal to something, x2 is equal to something, x3 is equal to something, okay? So all you would have to do is put comma, right, like comma sepal dot width is equal to, I'll just put mean sepal dot length okay. Oops, say it is case sensitive. It didn't like sepal width. It's not going to like sepal length either. Right, and there you go. So we predict that the petal length, or the average petal length, right? This is a confidence interval, average petal length for a flower that has an average petal width, an average sepal width, and an average sepal length. So basically an average flower, pretty much. So we predict that the average petal length of kind of like your average flower is going to be between 3.7 and 3.8. All right, I'm going to separate the lecture into another lecture starting here.